Hi, this is Blake Lehman, and this is my code for 8Puzzle. First, I've split up my successor function into two functions, available moves and generate children. Available moves will create a list of available moves and populate it with all four directions. It'll then determine the index of 0 in the provided board state, and then remove moves from the list of available moves based on that location. So, for example, if 0 is on the left side of the board, right will be removed since it's not possible to move something into the hole from the left. The function that called available moves will then pass its return value over here to generate children. Generate children will, for every available move, pass a parent state and a move to its helper function do move. Then it adds the kid and returns the list of kids. Do move calculates a new board state. Based on the board state and move from its argument, it swaps the 0 with the appropriate other value. It stores a value that moved into temp. It then returns a child with a new board and uses temp to assign it the appropriate path cost and total cost. Then we have my breadth first search function. Its queues are visited and ever visited. It starts by adding root to both. It then iterates over visited, popping here. It checks if the popped state is the solution and returns it if it is. If it isn't, then it generates its successors using my two successor functions. After generating the successors, it assigns it to be the current state's children. It then goes through the list of children and enqueues them. If they haven't been visited before, check visitation just iterates over ever visited and compares the board states there to the arguments. I went with a recursive algorithm for my DFS, so there's no explicit stack here. Instead, the global variables DFSQ count and max DFSQ count emulate this by incrementing whatever state is added to the ever visited list and by decrementing whatever state is returned. So at any given point, DFSQ count represents what the size of the stack would be in a stack-based solution. The solution is otherwise pretty simple. It checks if it's the solution. Otherwise, it generates successors. It assigns those successors to itself, but only if they've never been visited, and then recurses on the child. Finally, if no children were generated, it returns itself. This is my uniform cost search. It uses two array lists, active and visited. The following algorithms will do the same thing. Active represents states that have been generated but not visited, whereas visited appropriately represents only states that have been visited. So we first remove the current node from active and add it to visited. We then check if the current state matches the goal state. If so, we return. Otherwise, we generate children and assign them to the current node, and then in the same loop, check if each child has been visited before. If they haven't, we add them to the active queue. Next, we find out what state to visit next by searching through the active queue and finding the one with the lowest total path cost. Remember that my successor function has been instantiating each state with the total path cost derived from its parent. And finally, it recurses on that state. My greedy best first is similar to uniform cost. After removing the current node from the active list and adding it to the visited list, it checks for the goal. Down there. It then generates children, assigns them to the current state, and then checks if they've been visited. If not, it adds them to active, so that's just the same thing. But the difference is down here, where it decides on which state to visit next. Here it invokes how many wrong, which just iterates over the provided state's board array, comparing it to the goal array, and returns an integer for how many were different. It selects the state with the least wrong tiles and then recurses on it. My first A-star algorithm adds the root to the active list and then enters its primary loop over here. The primary loop searches the active nodes for the one with the lowest f. It uses the function f1 to determine that. F1 just determines, sorry, this down here. F1 just returns an int, which is the argument state's total path cost plus the how many wrong tiles from my earlier function. And once it's determined the state with the lowest f, it stores it in current. The current is removed from active, its children are generated and assigned. The algorithm then iterates over the children, first checking if they are the goal, and then returning them if they are. If it then searches the active list for other states with the same board state but a lower f. If it doesn't find any, it adds a child to the active list, and after doing this for all the children, it has the current node to visited and loops. Finally, my second A-star algorithm is virtually identical to the first one, so I won't spend too much time reviewing it. It does differ down here, where the function called to get the f of h state is f2. F2 returns the sum of the Manhattan values instead of how many were in the wrong spot. So once it's decided on the node with the lowest f value, it says the state is current, goes through the same process as A*1, though of course it does use f2 later when searching the active list for a state with the same board but a lower f. Finally, I'll show some code running. So this down here is my text interface. I enter an integer for algorithm. So here I'll put in 1 for BFS and then 1 for easy. Here is my output. And then on the other end of the spectrum, I'll enter 6 for my second A-star and then 3 for hard. Let's make that window a little bit bigger. And now here is the result, which is fairly long. Thank you for watching.